I'm Janet Newman and I work at CSIRO's Collaborative Crystalisation Centre in Parkville in Victoria. We grow protein crystals because we're interested in the shape of protein molecules themselves. And the shape of protein molecules is interesting because shape and function are related. And we know this at all sorts of levels. So there's all sorts of analogies you can use. You can think about different codes of football. You've got rugby union players which are big and broad, and you've got Aussie rules players which are long and lean, both footballers but very different. Or you can think of sprinters. Skinny runners tend to be long distance runners. Big beefy runners tend to be sprinters. Form following function again. And that same thing happens with our protein. So if we can see the protein shape, we can understand how it works. The problem that we have with proteins is that a protein is very, very small. So an individual protein molecule is about 5 nanometers across. Nanometer is 10 to the minus 9 of a meter, which means you need a billion of them to make 1 meter across. We can't use normal wavelength of light. We can't use normal light to see these things. They're just too small. So we have to use X-rays to see a protein molecule. But when we put a single protein molecule in the X-ray beam, we still can't see it. So we coax our protein molecules into crystals, and then we can put the crystal in the beam, and we can get information about the protein molecule and the actual atomic makeup of that protein molecule. Once we've got that information, then we can start to do things like work out how small molecules like drugs might bind to the protein, or we can work out what other proteins might bind to our protein of interest. Or we can see how things have changed when the protein has evolved over time, and we can see if we can understand evolution then on a molecular level.